Okay, we're going to define a new creature. It's called divergence. So what's divergence? It goes like this. Given a vector field f arrow, we define and define the divergence of f to be, well, we'll introduce notation as we do it, div of f. And what's this defined to be? It's actually the gradient symbol we had before, dot vector field. Okay, there's a definition. I know this looks funny at first. We will certainly compute examples, but we've introduced two things in this section already, right? So given a vector field, there's the curl of the vector field and there's a divergence of the vector field. So how can we remember? Well, we have some real fortunate situation here that the divergence and dot, there's a dot product here, both start with D, right? D for both of these. And then if you look at curl was the other thing we defined for vector field. Curl and, well, cross both start with C. Yeah, and earlier curl of f was defined to be the gradient symbol cross f. So this works out really nicely that we just get real lucky in English that the divergence is a dot product and the curl is a cross product. Okay, so let's go ahead and compute some examples. Let's take the vector field f of x comma y comma z equals the following vector field 2x plus yz comma xy squared plus z cubed comma x to the fourth yz. And let's go ahead and find the divergence of f. We won't even stick the parentheses around. Sometimes, we won't do that. So to compute the divergence of f, okay, this is gradient symbol dot vector field. And I know this is going to look funny first time around, but just hang with this. So that gradient symbol, partial derivative with respect to x, partial with respect to y, partial with respect to z, dotted with the vector field. Yeah, so 2x plus yz, comma xy squared plus z cubed, comma x to the fourth yz. This is really just going to be partial. We'll write out a little more than probably we will in the future, but it's partial derivative with respect to x of 2x plus yz. Okay, plus, it's this times this, right? And by times, we just mean apply the partial derivative in the next step. Then partial derivative with respect to y of xy squared plus z cubed plus, it just looks like what a dot product ought to look like. Partial derivative with respect to z of x to the fourth yz. Now let's just simplify this. We'll have here 2 plus 2xy, right, plus, and then the partial derivative with respect to z here is going to be x to the fourth y. Okay, so we took the divergence of the vector field f equals angle bracket 2x plus yz, comma xy squared plus z cubed, comma x to the fourth yz, and obtained what we obtained isn't a vector. You'll notice here there's no angle brackets, there's no ijk, and there shouldn't be. I mean, after all, it was a dot product, right? And we obtained the scalar field. That is a scalar valued multi-input function, multiple input variables. Okay, we got, let's just name it lowercase g of x comma y comma z equals 2 plus 2y plus, 2 plus 2xy plus x to the fourth y. Okay, we got a scalar back out of this. So the key thing to point out here is, unlike the curl of a vector field, which is a vector field, so just from this example we should see that the divergence of a vector field, of any vector field, is a scalar field. And why? Why a scalar field? I mean, it's a dot product, yeah? And you may recall from way back when, just looking at dot product when it was originally just defined for vectors, constant vectors, that the dot product of a vector and a vector is a scalar. Now, let's just take a brief moment to talk about an interpretation. Basically, the idea is, what is the divergence compute? So the divergence of f, right? So is at so what is the divergence? Again, try not to stress about this too much, but if you had a vector field representing water currents, then this would describe how much water moves away from a point. You know, maybe it's a point x comma y comma z in three-dimensional space, or point xy in two-dimensional space. Okay, to try to explain divergence a little bit in a nutshell, what would, for this vector field where the first component is x and the second component is y, what would the divergence at the origin be? Well, at this point, we can see that all arrows point outward. It's like there's an explosion that occurred here, and that should turn into a positive divergence. Now, if we had negative x comma negative y, then all arrows would point inward. And so right here, at the origin, there'd be a negative divergence. Just for a different example, let's just say we looked at the, let's see, how do we change? There we go. Change the scale just right so that the vectors don't run into each other. But here, the vector field, well, a constant vector field, that is, at every point, the vector that's output is 2, 0 in angle brackets. And in this case, no matter where you go, the divergence is actually the scalar 0, because as much water would be coming in to this point here from the left as would be leaving the point.